Hi everybody, I'm Chris Ganesh and this is CS361, Systems Programming. Today's video is about executable relocation. So what we saw in the last lecture was symbol resolution, where we find the individual symbols that each individual reference in our .o files was talking about. Maybe it was the wrong one, as we saw, but we still disambiguated and picked a specific symbol that we're going to resolve that individual reference to. So within this entire process, we're almost done. We're doing the last few things that the linker is in charge of, and that has to do with merging all these different sections from different .o files into one big final ELF executable. And we're going to update the symbol references to their correct runtime addresses in that executable file. This relocation process looks a little bit like this, where we have all of our .o files there on the left side of the screen, and each of them, if you recall, have all of these sections, but the important ones for our process right now are the text and the data section. So every one of these is going to have a text section that has the functions that have been compiled into machine code in that specific .o file. And as the linker goes through and it finds which pieces it wants to put together into that final executable file, it picks them all up. And it's going to take those in addition to a little bit of system code that we're going to talk about a little bit later on. And it takes them all and collates them into one nice new big text section where all of those individual functions are eventually going to live. It also has a .data section, a .bss section, all of those good things that we would typically have in a runnable executable. One of the important things that that system code has is that _start function that GCC just puts in by default. So if you've ever tried to compile a file down into a runnable executable, but you forgot to give it a main function, what you didn't see was a special error message that says you must have a main function in order to turn this into an executable file. What you saw instead was a garden variety linker error saying that it couldn't find the symbol main. Now, in the way back when you're just learning C, you didn't know, like, what does this mean? You couldn't find the symbol main. What does it even mean? And then your TA or your instructor would say, oh, that means that you forgot to define main. You need to have main in order to turn it into an executable. You said, oh, okay, that makes it special, right? But what makes it special isn't that main is this one specially named function. It just means that there's some system code that refers to it. So within the start function, it does a whole lot of bookkeeping to initialize the entire executable that we don't need to worry about right now. And then it calls main. That makes main a symbol, and that specifically in this situation makes main a reference. So this main function here isn't special in any way different than swap or sum or any other function that you've written and included into your file. It just so happens that the system code that gets included into your program is calling this function main. It has this reference to main. Now a .o file has this rel text and this rel data. It has a symbol table, and it has all the stuff that, as we saw in the last lecture, if we already know where something goes, we're just going to put it in the right section. Symbol table entries are the combination of the information we need to know about that symbol in terms of where it resolves to, as well as the information about what resolves to it. That's what lives in the symbol table. The symbol table is simply an array that has a whole bunch of these structs in it that has all the useful information that we're going to need to know about the symbols that are defined in this file. Now, let's go and take a look at an example of a file that we're going to compile down. So what I've got here on the left is a very basic example program. What I've got on the right is I've run my makefile, which compiled everything. Let's make clean. Let's run this one more time. So I have compiled sum.c, which creates sum.o. I have compiled main.c, which creates main.o. And I have linked those two together to create this program main. So I can obj dump -d on main. This is going to show me my fully compiled file. just nice and disassembled with all of the different functions that exist within it. I think there's quite a few in here because I compiled it with debug symbols. I can also obj dump on obj dump. I can look at the symbols in it. I can look at the symbol table. Let's make this a little wider so we can see it a little bit easier. I can see my symbol table. I've got my text. I've got my relocatable text. I've got my data. I've got my BSS. Now, if I were to do the same thing on regular main, it's going to have a whole bunch of other symbols in it. But note that it doesn't have these relocation entries. These have already been taken care of by that linking process. We've got our init section, our text sections. Our init section is where we jump to when we start running this program, when we turn it into a memory image to run. We've got our text where our actual program assembly language exists, and a whole bunch of other stuff that we'll learn a little bit more about later on. So another important aspect of using obj dump and readelf and whatnot is that these programs don't do like a huge amount of stuff. Fundamentally, what they're doing is they're turning a bunch of bytes stored in a file into human readable, but still effectively like a list of those bytes. So we can take this program apart. We can take a closer look at this in lots of different ways. The most basic, lowest possible level way to do so would be to just hex dump that file. So we can actually look at the raw bytes that are stored in the program. And this isn't going to be super, super useful to us. But if we start digging around, we might be able to find something relatively useful. So if we were like super hackers and we knew the ELF file format, we'd be able to read this and say, oh, okay, I can hex dump these bytes and I can understand what's going on. But I can't do that. What I can do is start digging around just a little bit to kind of get an idea what the heck is happening. So I do know that this program starts with a 55, 48, 89, and lo and behold, I look here at address 40, hex 40. I see that 55, 48, 89. So the text of this program main starts here, and it's relatively short, right? It ends at that C9, C3. So this is the entirety of main. It's just a bunch of bytes. But when I look at it in hex dump, it's not super useful to me, right? I don't know where one instruction ends and another instruction starts. I don't know what the opcodes are and what x86 instructions they correspond to. And so that's where things like obj dump and readelf really come in useful. They actually show us what the heck is going on when it comes to humans interpreting these files. So that's a really useful thing here. Now, another useful thing that we can see is that I'm trying to call a function. Like if we look at this assembly code and we think back to 261, see that call queue is supposed to be it's supposed to be jumping to an address. But right here, it's saying, no, we're not jumping anywhere. We just have a bunch of zeros. So here we move into this one address, the value 2, because that's one of our arguments to this function. And then we're supposed to be moving array in, because we push things back to front. We push array in, but this is just a bunch of zeros. We call sum, but this is just a bunch of zeros. This is what a .o file looks like while it still has its relocation entries not yet fixed up. We just put a bunch of zeros in there, and we put some pointers later on that say, oh, hey, at 13 up from the beginning of main, you got to go fix it and add in sum. At E bytes past the beginning of main, you've got to fix the variable name for array. So what's important for us to see here is that this is not yet fixed up, right? However, if I go and I disassemble regular old main, and I come down here into the text section, and I find the code for main. Yeah. So I find this code for main. All of a sudden, once we've compiled the program and then linked the program, yeah, we've still got this 2 here, the same as we had before, But now we have an address for array and we have an address for sum. So that is the linking process and the variable relocation process taking place. So we want to look at if we look at the relocation entries for this file main.o, we can find the things that need to be fixed up. Here we've got two different variables that need to be fixed up. We've got a reference to array and a reference to sum. The reference to array is of this type absolute. So this is an absolute address of array, and this is a PC relative reference to sum. So when we have an absolute reference, we're saying we need to jump, or we need to refer to an address by its specific value. And because we're using this small code option by default in GCC, even though we're on a 64-bit architecture where full legal memory addresses are 8 bytes long, most of what we're doing when we have a relatively small executable is going to be below the 2 gigabyte boundary, and we can actually get away with using 32-bit pointers to refer to specific locations. So we can refer to array by the specific location within memory, and then we can refer to sum not by a specific location, but in a PC relative fashion. There's a lot of addressing that happens on all modern computers where rather than talking about specific locations in memory, we say, I know that the program counter, when I execute this instruction, will be at this location, and I'm going to tell it to go this far up or this far down from the program counter, and then I will find the variable I want to refer to. Remember, the processor has a lot of really easy addressing modes, right? If we go back over to our 261, we got lots of different addressing modes that the processor itself understands. We can talk about our absolute modes, our register modes, where we use a register to refer to a specific address. And then we've got our PC relative, then we have our relative addressing modes, where we say, based on a specific base, we want to move forward from that base. Now, in 261, we think about that in terms of looping. We think about that in terms of referring to an offset from an address of the base of an array. And that makes a whole lot of sense, and we're going to use that in this situation. But we're also going to use this relative addressing to talk about being relative to a specific location of the program counter, which is super useful. So the name of the game here is relocating symbol references. We're going to take this .o file. We're going to turn it into a fully ready to run executable. That fully ready to run executable cannot have these placeholders in it that say, eventually, when you put everything together, remember, like this, no, like this, the relocation. So relocation is, if we can recall from this slide, let's get rid of all of our ink real quick. So if we recall from this slide, this is the first step of the entire relocation process. The first step is to take all of those individual text sections, all of those individual data sections, and smush them together into one nice big text section and one nice big data section. Now we can kind of see why we had a bunch of placeholders there. Those placeholders were because we're going to move all of this stuff around, and whatever address I used to have for my data in main is no longer where my data is going to be. Just like in my sum.o, that text is no longer going to be where I expected it to be. It's going to move around. And for the case of using swap from main, I didn't even know where it was in the first place. So now I actually have a chance to use it the way that I wanted to use it. So let's come back over to our really basic compilation example. Just as a quick reminder, we've got this main file. Let's change this so that we can see a little bit more. So we've got main, and we've compiled main. So main has a bunch of text, and we can go dig into, so remember, so object dump is just a way to look at the hex file, to look at the, so obj dump is just an easy way to understand what those bytes of an ELF file mean. all we're really doing is adding a little bit of extra annotation around a hex dump of main.o. So if we hex dump main.o, we're going to see every single byte that's stored in that file. And if we scroll through and look in the right place, we'll see the actual code of main. So the code of main is 55, then 48, then 89, then E5. And those things start here. So 55, 48, 89, E5. This is where main is. This is actually the entirety of main are just these bytes. But we don't see where one instruction ends and one begins. We don't see what the actual instructions are. We just see opcodes. That's not nearly as useful as what the output of objdump gives us. This actually lets us see all these different addresses, and it also gives us this very important part where we have these relocation entries. So the really important part that's coming out of that rela text is at E offset from the beginning of main, we have an absolute reference to a memory location that will eventually be the global data structure array. Likewise, at 13 offset from the beginning of main, so we can count up our addresses and count in hex, this is address 13, we have a 32-bit PC relative address that is eventually going to be the value of wherever sum's location is minus 4. That's going to be important. So let's do the easy one first. If we're trying to do the relocation for array, the first step is what we see here, where we take all of these things and we clump them all together. So once that clumping them all together happens, once we've done our symbol resolution, the linker is going to find a specific version of array, and it's going to put that version of array somewhere in the data section. It puts that array in the data section, and now it knows, okay, array has a real honest to goodness location. I need to go back through and follow my algorithm to figure out what to put there. I'm going to do that by iterating through my relocation entries. I'm going to find the one called array and say, aha, I've got to fix this. And how am I going to fix it? I'm going to find the exact address that I put array in, and I'm just going to replace, starting from address E offset of main, that new address. So if we objdump the full version and we look for array, so nope, yes, this one. So this variable array, so this is the full symbol table for the executable. This is the fully linked executable. So before we had the fully linked executable, we took all of our global variables and we said we're going to put them into the right place in the data section. And this one in particular, it goes into the data section and it's going to go at address 601030 and it's array. And so now if we come down here to main, we see that we went to E offset from the beginning of that. So that comes down to here. And we put the little endian version of 601030 into there. Ta-da! We have done an absolute relocation entry. We fixed it based on what we knew from the text section and what we knew from the data section and what we knew from the rela text section, the relocation entries for the text. Now, the next one that we need to do is this PC relative relocation entry for sum. Now, there's two parts here that get a little bit trickier. The first part is that this is PC relative. So what that means is that rather than computing the exact address like we did for array of just where within the entire program we are, instead, we're going to say, I want to find where this symbol is in relation to where the program counter is going to be when I'm running this instruction. Now, this is where things get a little bit weird and a little bit annoying because it doesn't make too terribly much sense. But the important thing that you just have to trust me on and remember is that when you are running a specific instruction, the program counter has been set to the first byte of the next instruction that you need to run. So when you do this relocation, you're going to have to take into consideration where you are, where the program counter is. You're going to take into consideration where the target of this relocation entry is. In this case, it's going to be the beginning of that sum function. We need to find the difference between those two addresses the moment that you are dealing with that reference. And if you're running that instruction that's at address 12, your program counter is going to be set to 17. That's just the way that x86 works. We just have to remember that. So we're set to that 17, and when the linker has done the task that it has to do of globbing all of the main and swap and sum and yada, yada, yada all together, we need to find the distance between that 17 and the very, very first byte of sum. Once we have that distance, we're going to place that distance at 13, but not quite yet. We've got to place that distance minus 4 into that location. We have to do one last modification to make it actually work correctly. Notice that this isn't just saying put sum in there, put sum minus 4 in there. Now, why is that? In PC relative address land, we can't just say go from 13 to wherever sum is and call it a day, because the program counter isn't actually set to 13. Like, the program counter is never going to be set to 13. The program counter is always only set to the first byte of every individual instruction. So the program counter is going to be 12, then it's going to be 17, then it's going to be 1A, then it's going to be 1D, etc. So when we're on this specific instruction, one important thing to remember about x86 is that the program counter will be set to 17 while we are executing the previous instruction. The program counter always points to the next instruction. Just a thing you have to remember. So if the program counter is pointing it at 17, then we can't just take the difference between 13 and wherever sum is. The difference between where 13 is and where sum is not going to give us the correct relative address. So the linker uses the addend to modify the value that's being stored into that placeholder. So the first step that the linker does is it finds the difference between the location of sum and the location defined by the relocation entry, which is 13. So say sum was 20, we'd say 20 minus 13. That is A, I think. I don't exactly remember. I'm not good at math of the computer variety. So let's say we're in hex. So just 20 minus 13, D, yeah, whatever, I was way off. So 20 minus 13 gives us D, but that's not going to be right? That's going to give us the distance between this byte and the first byte of sum, but we want this byte and the first byte of sum. It just so happens that the compiler was helpful for us, and it said, okay, well, here's where the relocation entry is, here's where the PC is going to be. They're 4 bytes away from each other, so put a addend in here of 4 to fix up the value that goes in. So once you find the distance exactly between this value and the beginning of sum, subtract 4 away from it. So make that distance 4 smaller, because we know that sum is going to be there in front of it. After we've done that, we're going to put that value into that area 13. So if we come back over here and take a look at the fully compiled version, and we find sum. So first off, sum is a symbol which exists in the text at address 4004B6. And if we come down here to the call, now here we have smooshed everything together. We see main is here, and the very next thing is sum right after it. And we see that we are calling to 8000000. And what that means is that if we take this address, 4004AE, which is where the program counter is going to be, and we subtract that from 4004B6, hopefully that'll give us the value 8. So 4004B6 minus 4004AE, 8. 8. Awesome. That is exactly what we expect it to be. Now, that's one use of the addend, which is a little bit of a complicated beast, right? So our addend here was -4 because we needed to subtract 4 off to change the value which got inserted into the assembly code of the fully linked executable. That's not the only way that we can use the addend. The other pretty useful way that the addend can get used is if we wanted to, rather than refer to array, maybe I wanted to refer to array sub 3, right? So maybe I wanted to take that value. So let's say I'm going to save this. I'm going to GCC it, GCC C main.c, and I'm going to obj dump main.o. Our previous version, let's see if we can scroll all the way back up to our previous version, was array just all by its lonesome. We're saying we exactly need to find the exact value of the symbol array, the location of the symbol array, and just shove it right into address E offset from the beginning of main. Here, instead, we're going to look for C offset from the beginning of array. One question that I think would be fantastic on an exam, and certainly fair game in a discussion situation, is why do we even use that? Like, if we have this ability to talk about specific locations, what's going on there? That's a great question. We can answer it. It's a little bit tricky. I think there's a good hint in the book, but a good food for thought is, why do we need to use these addends if we could just find exactly where that location was and shove it right in? And I'll leave that for you. That's about all I have for today. Thanks so much for watching, and I'll see you next time.